Okay, so before the break, we were doing a bunch of conversions. Binary to decimal, decimal to binary, the stuff from the other day, talk about fractions. Then we saw the hexadecimal, which we use to makes conversion between binary and decimal easier. And if we have to work in binary, we can use hexadecimal and work in at 4 bits at a time. And we saw all those conversions, but well, everybody in this room is IT people, right? We use technology. So obviously technology can do this for us. Most calculators have this functionality built in. The one I grabbed here to point at is from the Dollar Tree. So it's a $1 calculator. Probably doesn't, probably doesn't hurt to spend $1 for something sitting in your desk. That way you have one, they're handy. Also, it's a Dollar Tree, so you might, I think the last time I went and bought one, I bought 5 because it's the Dollar Tree. But most calculators will do this. If you have one you like, you can use that. On the ones from the Dollar Tree, here above our math operations, you can see it. There's a binary, octal, decimal above these things. So this will do the conversions. So like, oh, those numbers I just erased from the board. Probably could have left them up there. I'll just make one up. But if I put this in, well, I'll start with a decimal number. So 54, and I just turned the calculator on, so it's starting at 54. If I push second, and then the division on this one turns it into binary, there's that binary to decimal conversion. And I'll clear that, and it's probably hard to see, but the little BIN is still up there at the top, so it's in binary mode. So most of the number keys don't work now. I can push a bunch of numbers, but the only ones that are going to work are the 1 and the 0. 1 1 0 1 0 0 1 1. That's kind of hard to do backwards, but when in binary mode, it'll only enter the 1s and 0s. And then if I push second, and you can see there on the plus sign, it has the DEC for decimal, and switch back to decimal mode, it'll do that conversion from binary to decimal. Or above the minus sign is hex. So I can do second hex and see that that number is D3 in hex. And obviously it's a different place on every calculator, but if you can see it above there, there's an A, B, C, and D. There's a symbol somewhere on there to enter the hex values. So most calculators will do that for us. Or if you're sitting by your computer, if you're going into IT, you're probably going to want to have a good text editor around. If you're doing some sort of software development or something where you'll be doing lots of programming, you're definitely going to want to have a good text editor around. So I'm just going to point at one of those. I'm going to share my screen. One that's been very popular for many decades now on PC things. Oh, whoops. Yeah, that's several people's names are already on that list. That's the extensions for the homework deadlines. Like if you need a little bit more time on the homework, since I accidentally left that open, if you need a little bit more time on the homework, I just put your name on a list. And if it's something that closes, I'll open it back up for you. But most of the stuff doesn't close immediately. So if you just need a couple extra days to finish it up, I put names on that list. And then the computer applies the late penalty, and I'll come back and take the late penalty off later. So if I ever told you there was a couple more days to do something, and you see the computer applied that late penalty, I will get it as soon as I see it. I go through that every couple days. Seems like a good time to let y'all know that, but I just keep that on the list. What's this? Oh, I don't need to keep that. And what's on the screen right now is, well, I might need to keep that. That's a language called Latex. It's a markup language used for formatting mathematics. To get all the nice formatting of mathematics, we use what's called a markup language, where we just put extra little symbols that say what kind of data we want or what symbols we have. That's a common one for doing mathematics. I probably shouldn't just, well, I know LaTeX really well. I don't need to say that. But if you're going into IT, you're going to want a good text editor. Right? Your PC probably has a generic one like Notepad, just regular Notepad, where we can write text, and that's about all. The one that's just ASCII code coming in and out, which we're going to talk about ASCII code next week. I was planning on it Monday, but I guess we'll do it the first part of Wednesday because Monday's a holiday, 3-day weekend, but just a basic text editor. There's no fancy features in Notepad. If you're going into software development, programming, we've already seen that with Python. That's just a text file. And we just write some text, and then the computer converts that into a machine or assembly language that it knows what to do with later. So we need a place to write that text. So one that's been very popular for several decades on Windows machines is Notepad++. If you just want to try some out, you can go on Google and look for good text editors, or if you want a list of some, I have a list. I can send you a list of some good ones and talk about advantages and disadvantages. I just opened this one up. It's been popular for a while. If I come up here to language, you can see the list of programming languages that this knows is too long to even fit in one spot. We have this whole alphabet full of languages. So I'll go to Python. Perl, so P-E-R-L, Perl, that's the language that Raptor was originally written in. So if at any point this semester, which I think I've already done it a couple times, I say something referring to the Raptor flowchart interpreter as a language, I'm actually referring to Perl for, because that's what Raptor was originally written in. There's also an object-oriented Raptor, which was written in Java, so they behave differently. But that's the language I'm talking about whenever I say that. This knows Python language, so it has all those things we've seen, like the predictive text, which I have turned off because I use this for class examples, but things change colors. Got the color changing to recognize the language, and it has predictive text, which I have turned off here, and things to help write code. So you might want to look for a good text editor. If you're going into IT, you're going to need one at some point, so you might want to start trying them out. But the reason I opened this now is that most of them, the nicer ones, have some sort of plugin or tool to do the conversions. So Notepad++ has this converter panel, ASCII to hex, hex to ASCII, which we're going to talk about ASCII next week. But, whoops, I didn't mean to dock that in there, but that's fine. I was just trying to get it over on the screen. So we can enter a number, and this will automatically give us the other one. So like 123. Well, you saw how quickly it was doing that. It was changing as I was typing, unless the video is lagging. But decimal 123 is 7B in hex, or 1111011 in binary. And well, we just set up a one-to-one relationship between our symbols and the numbers. So number 123 in ASCII, as well as Unicode, is the opening parentheses. Or if we wanted 67, see, that's the symbol, that's the number that represents C. So that's how we store our language. We just do a coding. We say, okay, 65 is an A, 66 is a capital B, 67 is a capital C, 97 is a lowercase a, 98 is a lowercase b. And then we see those hexadecimal values. So 98, the number 98, like we're used to in decimal, is hexadecimal 62 or binary 110010. So there are lots of tools out there to do those conversions. I wanted to point at that and mention text editors. So the tools are available, but I do like to ask that on that quiz where there's some conversions this week, the module 3 quiz has some conversions. please try to do that by hand, because those are probably the only ones you'll ever have to do by hand. The rest of your life you can use technology, or some parts of IT don't necessarily won't be doing a lot of that. So technology exists, but please try it by hand first when you do the quiz this week. I think there's unlimited tries on it, so you get multiple tries. But lots of technology to do it, including the calculators they sell at the Dollar Tree for $1, useful things to keep in the desk. So that's how we represent our numbers. And we're going to talk about it more next week, but that's also how we represent all of the other symbols on the keyboard. The space bar is number 32. The W, the exclamation mark, the 4, the 5, all those symbols that we normally use for our language, we just store those as a number. So the computer's still working with numbers, keeping track of numbers. But we need to do some math with numbers. So that's the next thing on the list. Just kind of dealing with those numbers. This other day, something that you don't have to do, just to show that the bases are all the same, we went through the number system and added and subtracted and multiplied things out by hand, right? That was just to show that it's the same process, just with a different base. The numbers still work the same, but we had those different operations. We had some adding, subtracting, multiplying. We didn't really see it, but division. I'll use the Python symbols. We usually have integer division and modulus division, which gives us the remainder. That way we can get the quotient and remainder when we divide. We have a bunch of different symbols. So when we build the machines, we don't want to put circuitry together for every one of these, because that'd get complicated, right? And we can simplify it a little. So modulus and division, that's really one operation. We'll call that dividing. And multiplying, you probably remember from your math class somewhere along the way in your education that multiplication can be viewed as really just repeated addition. And in the same way, division is kind of repeated subtraction. And if we subtract repeatedly, eventually there's going to be some left over. So those are just repetitions of adding and subtracting. So if we take those two off the list, there's only 2 operations we'll need to do. But it'd still be nice to do if we only had to build one circuit that could do both of them, right? And you probably saw somewhere along the way that that is how we should think about our numbers. Because when we draw a number line, just using some base 10 numbers, we usually put 0 in the middle. And then we have our positive numbers, 1, 2, 3, positive numbers going off to the right, and negative numbers going off to the left. So if we have something, and when we have something like, say, 17 minus, horizontally, minus 7, at some point in one of your math classes, you probably heard that we often want to kind of simplify our processes. And even though we're doing the same steps, it's better to think of that as 15 plus a negative 7 whenever we have subtraction. Does everybody remember seeing that somewhere before? So instead of add and subtract, then we only have one operation. We have add or add the negative. We have add the positive or add the negative, but only one operation, which is really nice when we go to build a machine, because then we only need one circuit to carry out that one operation. So what we need is a way to define negative numbers in binary, so that we can do that all in one circuit. Does that, what we need there make sense? You may have any questions about that lead in? Anything you forgot about? Yeah.
Oh, no, I was just saying, no, I had no questions.
Oh, okay. Yeah, hopefully that makes sense as far as why we need a way to define negatives. Because in our base 10, we just use the negative symbol. But in machines, we don't have a negative symbol, do we? We don't even have a positive symbol. What symbols do we have for our machine? Just the two, right? It's like a switch. It's either on or it's off. So we only have the two symbols, and we're already using those for our numbers, but we don't have another symbol we can use. So to start with, we want to use one of those, and we'll just define it. Let's define 0 to mean positive and 1 to mean negative. So then when we write an 8-bit number, our first bit becomes the sign. So we drop our 2 to the 7 column and make that a positive or negative sign. And then the rest of the columns will still be the same. 2 to the 6th, 2 to the 5th, 2 to the 4th, or 16, 8. Cool. That should be a 3. 2 cubed is 8. 2 squared is 4. 2 to the 1st, or 2 to the 0 column. So we lost some of the values we could hold. With 8 bits, we were able to go from 0 to 255, but we got rid of one of our bits. So now we can only go from 0 to 127. But we have we can do that positive or negative. So actually, we could go from a very negative, 0, 0, 1, 1, 0, 0, 1. Somebody want to tell me what that number is? Just a little bit more practice before you take the quiz for this week. Oh, I saw the thing light up, but
Is it 21?
a little bit more than that.
Oh,
I think you added the next column. So here we have a 16 plus an 8. I think you were adding 4 to that. 16 plus 8 plus 1 would be a 25, right?
Yeah, it's 25.
No worries. That's what we were talking about right before the break. Binary is really hard for humans. That's why we normally would break it into 2 chunks and do the hexadecimal if we have to work with all those bits, because 2 symbols just isn't enough for a human mind. We can deal with so much more than that. But we can do either a positive 25 or we can do a negative 25, which really gives us numbers. If all these are 1s, we can go from negative 127 to positive 127. So we still have 255 bits with 255 values we can hold, but we have positive and negative ones. So we can add them, so we can consider them that way. But there is a slight problem when we do this. I'm going to erase a couple of these 1s and write 6. And if I erase the sign bit, so that one's easy. What number is that? We don't have anything in any of our columns.
Yeah, 0.
So yeah, 0. So then we go plug in the sign bit. So that's saying positive 0. And that's saying negative 0. Which isn't really an issue, because that sometimes shows up when we're doing math, right? We start simplifying columns and equations, and we'll see +0 or -0, and then we just know to ignore that part. Unfortunately, a machine can't ignore a part, but there is a technicality there that's an issue, right? Because how many zeros do we have? I drew that number line up there a minute ago. And for any number, we have a positive pi and a negative pi. A positive 6 million and a negative 6 million. So we have two of all of our numbers, except for the one right in the middle, right? We only have 1 0. So doing that gives us a bit of a problem. It works for nice if we're just categorizing things, but that technicality gets in the way of building one single circuit that can do all our operations. That can add the negative, because, well, having 2 zeros is an issue. It's actually called the zero problem. So we need a way to fix that. So that's called sine and magnitude system. Sine and magnitude. So you can see it's not a very creative name. It has the sign to the number, either plus or minus, and then the magnitude of the number, how much the value of that number. But it has problems, but it's also quick and easy. So we do sometimes work with that if it's going to work. But that's not going to work for our circuitry to do math. Is it okay if I erase this and look at what we actually do use? And yeah. I'll leave the name up there because there might be a question on the quiz that has the name, refers to sine and magnitude. So remember, sine and magnitude is we just defined one of our symbols to be plus and one of them to be minus. And then we can get all our positive and negative numbers, but we also get 2 zeros when we do that, which is a problem because, well, we only have 1 0. That's the only number we only have one of. We don't have two versions of nothing. We either have nothing or we have something. So there's lots of somethings, but only one nothing. So another way to work around that is to use complement. In particular, 2's complement, but we have to talk about 1's complement in order to get there. And I believe there's some questions on the quiz about 1's complement, or in the bank of questions the quiz pulls from. So you might get the question. So 1's complement. And it is complement with an E, not an I. We're not saying nice things about our number. The to completion definition version of complement, the one with 2 E's and no I's. We're not saying nice things about numbers. Actually, the completion, which complement means the rest of them. Anybody ever heard that term used before? You may have heard it in your art class, the complementary color. So like in elementary school art class, complementary colors are the ones opposite each other on the color wheel, the ones that mix together to give shades of brown, blue and orange, red and green. They're kind of opposites of each other, but it's halfway around that wheel of colors, so it completes it, the color that completes it. Or in the case of like a Venn diagram, where we have a collection of stuff we'll call A, a collection of stuff we'll call B. This bubble represents, whatever we have in there, maybe some numbers, some set of things. Then there's the stuff in A, and then the complement of A is everything that is not in A. So like everything in this set over here, B, or everything that's not in either one of those sets. The rest of it, the remainder of it, which is really nice with binary numbers because we only have 2 of them. So the only thing it could be is the other one. So the complement of a 1 is a 0, and the complement of a 0 is a 1. So in binary, the complement, the completion version of complement with an E, not saying nice things about 1s and 0s, just complement means the other one. So whenever we have a binary number, so let's take 62. Somebody tell me how to write 62 in binary? Do I remember how to write that? Are you working on it? Or we've already talked about that in class. I think it's in the calculator, right?
I was gonna say a couple of people put them in the chat.
Oh, did they? Oh, yes. Yes. So 62 is no 128, no 64s. We'll have a 32, a 16, 48, plus 8 is 56, plus 4 is 60, plus 2, plus 0. That should be a 62, right? Thank you. I didn't see it in the chat room. I glanced at it a moment ago and it hadn't quite popped up there. So whenever we take the complement of that, the 1's complement, so we're still kind of want to think about that sine and magnitude thing we just started with. That's why I picked a number that used less than 8 bits. Then we can do the sine and magnitude and have a positive 62 is a 0. So that first bit does matter. The complement is we just switch all those 1s to 0s. So our 1's complement of that is 1, 1, 0, 0, 0, 0, 0, 1. That's straightforward, right? Just switch all those. And, well, can we call that a negative number? If we switch all those, switch all the bits, well, that sign bit, that kind of works like a negative number. And then we have something different that might give us a nice pattern to work with when we put circuitry together. But if we do that on 0, I'll just do a 3-bit 0. If we do that on 0, we still end up with 2 versions of 0. So we have too many zeros. So to really get rid of that 0, we want to go to 2's complement. Where we, first off, take the 1's complement and then add 1. So we take whatever our number is, write out all the bits for it, and then we get the complement of it. All the 1s become 0s and all the 0s become 1s. And then we add 1. So we saw this the other day. 1 plus 1 is 2, or in binary, that's 1, 0. So a 0 will carry a 1 to the next column. 1 plus 0 is a 1. And then everything else is just kind of plus 0. So everything else is just going to come down. And then that adding 1 back, you think of it as like writing all the numbers out on the number line. I guess my hands are moving in the like a vertical number line, and then taking all those negative numbers and shifting them up by 1 to get rid of that extra 0. And then this 2's complement is makes it very easy to build circuitry that can do math. And we'll see some math. But everybody get that process wrote down? And then we'll go through a couple examples real quick here. So we take the 1's complement and then add 1 to get the 2's complement. And then that gives us a negative number we can work with. Is it okay if I erase this? We can do some quick examples.
Yep.
And I'm, like we were doing the other day, I'm going to use 4-bit examples because it takes forever to write out numbers in binary on the board. And it gets really hard to follow. So for examples, I'm going to do some 2-bit numbers. So 1's complement, we just complement the number. And 2's complement, we take the complement and add 1. So let's say, well, let's do adding like we did the other day. And then we can do all our stuff with adding. So just a refresher on adding, I can't remember what numbers I did. So let's do 8 plus, well, that would give us 15. Oh yeah, that'll work. I'll do 8 plus 7. So 8 in binary, just gonna do 4 bits is, well, we have 1 8 and we have our numbers, so we don't need any other columns. And 7 is 1 less than that. So we can't have any 8s. Then we have a 4, leaves us 3. So we'll have a 2, and then we'll have a 1. And when we add these, we just go right down our columns, just like we do in base 10, only we're adding 0 and 0, 0 and 1, or 1 and 1. And if we have to carry, the most we'll have to add is 1 plus 1 plus 1 to get up to 3. But in this case, it's 0 plus 1 every time. So just like we have in base 10 math, we can add down our columns and get that. If we want to subtract, we need to use 2's complement in order to get the negative. Because everything else, when we try to just try to symbolically add a negative in there, we end up with that extra 0. So we'll do the same thing. So let's do 8 minus 7, which I guess really I should write as 8 plus negative 7. We want to do it this way. So 8 we saw is 1, 0, 0, 0, and 7 is 0, 1, 1, 1. So to subtract, the first thing we do is take the 1's complement of the one we want to be negative. Our 8 is still positive, right? So it's just going to copy over. 1, 0, 0, 0. And what do we get for the complement of this number?
1, 0, 0, 0.
Yep. That gives us our 1's complement. Then we need our 2's complement. To get the 2's complement, we add 1. I ran out of room. I guess I'll put it down here. Then our 2's complement, well, our 8 is still positive, so it's still 1, 0, 0, 0. I'll put a line to separate all that. After this, we went down here to get the 2's complement. I should have paid more attention. I was going to try to write that all in one big long row. And 1, 0, 0, 0, so we have our 1's complement and then add 1. So if we add 1 to that, 0 plus 1 is 1. And there's nothing to carry, so none of our other columns are going to change. So now we can add those together. An 8 plus a -7. 0 plus 1 gives us 1. 0 plus 0 gives us 0. 0 plus 0 gives us 0. And 1 plus 1, again, is 2, which in binary is 1, 0. Which looks like too big of a number if we take 8 minus 7, right? But remember, we're working in 4 bits here. So this 5th bit, just gets discarded. Yeah, for purposes of this class, we'll say this bit gets discarded. I know at least one person in the course has said that she's moving on and planning on doing a computer science degree at another school after finishing at Ivy Tech. So that bit is important for, like, next week, we're going to start looking at selection structures and conditions. And when we're working in machine and assembly language, we use that extra bit to know when it's time to know if our number was bigger or smaller. That's how we make a comparison. We subtract and see if there's something left over. We get a Z when we subtract, but that's further along. So it does get used. That's for those continuing on to like computer science degrees or something. That's the bit we'll use for jump on carry when you get to assembly language stuff. But that's way down the line for this course. I'll use a term I don't think I've used yet in this course. It's beyond the scope of this course, which you will hear me say that periodically. And when I say beyond the scope of this course, that means it's not in my lecture notes. It's still up. If that's something you want to ask questions about, we can address the questions. But that extra bit, we will always have an extra bit when we do this. So that's when, for those moving on to computer science degree, when you get to assembly language, that's the bit used for jump on carry. But way down the road for, or a little ways down the road for the people that are going to get there. We just always have that extra bit. So if we discard that extra bit, which is what happens in a circuit, right? Remember, this is electricity. So that extra little bit of voltage is just going to feed back to ground. It really does get discarded after we take note that it's there, if we're going to do anything with it. But after we discard that, 0, 0, 0, 1, we have a 1 left. And 8 minus 7 should be a 1, right? So you can see that pattern worked out. And that is one that's definitely in the quiz. And this is how machines actually operate. So I want to do a second example of this. Does that make sense to everybody, the steps? And there are some in the quiz. So get your numbers. Take the positive one will stay positive. And the negative one, you take the 1's complement and then add 1 to get the 2's complement. Is it okay if I erase this for a second example? Hopefully that's making sense. I assume the silence means it's okay.
Yep.
Yeah.
And this is important because this is how machines actually are. This is what the machine actually does. These are the circuits we've built. We built a 2's complement system because it's really, really easy. I have a video that walks through the electronics part on my YouTube channel somewhere. What did I call the playlist? I think if you check my YouTube channel, the link might be on our Ivy Learn site. I have a playlist called Removing the Mystery. And there is one that walks through the electronic circuitry of that, how that actually works in the electric circuit, if you're interested in that. All you need to know for this course is how that works. So what's another thing we could do? Let's take 13 minus 4 is what we want to deal with, which really, we need to do that all as one operation. So really we want to do 13 plus a -4. So how do we write 13 in binary? Let's just do 4 bits again. Is there anything in the chat room this time? Somebody want to tell me how to write 13 in binary? Or we can just talk it through. Do we have any 8s in the 13?
Yes.
Okay, so that will leave us 5.
And we have
next
4.
4. And that'll leave us 1. So we don't need any 2s and a 1. And then a 4. First off, we just find our regular integer representation of it, which, well, we don't have any 8s. We have a 4, and that's the number we're actually looking for. And zeros over there. And then to do the subtraction, we want to take the 1's complement and then add 1 to get 2. So to get our 1's complement, well, our positive number stays positive, 1, 1, 0, 1. And what's the 1's complement of this? Somebody want to tell me?
Somebody type it in the chat.
So if we take the 1's complement of this, what's, oh, it's in the chat. Oh, yes. Thank you. I was looking, but then everything above it is also there. So yes, 1, 0, 1, 1. I didn't notice the chat move. I guess it popped in and then everything rolled up and I couldn't, all the bubbles were the same size. So that's our 1's complement, which is really easy in binary because this pattern, 2's complement, works with base 10 numbers. The complement is the digit we have to add to get to our highest number, which still fits this definition, right? We only have 2 symbols. So to get from 0 to a 1, our highest digit, we add a 1. And to get from a 1 to our highest digit of 1, we add a 0. Really easy in binary. That's another way of stating the complement. But when we do that on base 10 and have the 9, try to get back to a 9, and then have all the different symbols, it doesn't, 2's complement complicates it. It doesn't make it easier. But again, it's not necessarily a computer thing. It's a older math concept that was just applied in computers because it solved our problem. So to get our 2's complement, we need to add 1 to this, which, whoops, I'm just going to do right here. So plus 1, then our positive number is still just a positive number, 1, 1, 0, 1. And our negative number, we got the 1's complement, so we add 1. 1 plus 1 gives us 2, or 1, 0 in binary, so 0, and we carry a 1 to the next column. And 1 plus 1 is 0, carry a 1 to the next column. 1 plus 0 is 1, and then we have a 1 here. So our 2's complement for that is 1, 1, 0, 0. And now we can do that single operation. Almost did that without having to grab another piece of chalk. 1 plus 0 is a 1. 0 plus 0 is a 0. 1 plus 1 is a 0. Carry a 1. 1 plus 1 plus 1. Well, that's as much as we'll ever add in binary. That gets us all the way up to 3, right? Which in binary, 3 is written 1, 1. So once again, we're working in 4 bits. So we just discard that highest bit at this point. For those who continue on and start working and learn to work in assembly and machine language, that's carry. So that's very important for working in machine language to know that bit's there. But for us, we're just going to call it discard. it's electricity, so we send that little bit of voltage, that extra electricity back to ground. Like, yeah, we don't need that part. We just need 4 bits. So 1001, what is that? What is that number? How would we normally say that?
9.
Yep. And is that the right answer for 13 minus 4? So you see that pattern works out, and then it gives us a way to do addition and add the negative, and then multiplication is just repeated addition, and division is repeated subtraction. So we can just keep repeating that process, and then modulus, the remainder, that's just repeated subtraction and whatever's left over after we're done subtracting, when we can't subtract anymore. So that builds up all of our math operations from one circuit. So that's why that one's important. That is the way we actually, that is what the ALU does. The ALU is typically called a full adder, and it either puts 2 positive numbers together, or it runs through some inverters to get and it does some stuff to get the 2's complement and puts a 2's complement with a positive number. So that's what that ALU and, well, the FPU does a very similar thing, but that's how the processing is actually carried out, using 2's complement numbers. Does anybody have any questions about that? So we get a 2's complement number. So the question just popped in the chat of what happens for 4 minus 13. So we have both of those here. So I'm going to flip those. Our 4 is the positive number. A little bit more complicated of an example, but it only takes one more step. So our 4 is the positive number, 0, 1, 0, 0, and our 13 flips, 0, 0, 1, 0. Well, the last one's a 0, so when we add a 1 to that, we're going to get a 1 there. So 0, 0, 1, 0 plus 1 to get our 2's complement, and then we add these together. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. So we get that, and then that extra bit, this kind of gets into how the machine works. So you might remember, I think on the first day, maybe the second, I explicitly stated that for this class, we are going to say 1 means on and 0 means off, because we're learning how to process binary code, but that's not exactly what happens on the machine. The technical terms for electrically is 1 means we're going to source the current, and 0 means we're going to sink the current. So we have a circuit and we have something going on over here. The oversimplification of that is we can put our switch on this side and use positive voltage feeding in, and that's a 1. That's called sourcing the current. And again, this is an oversimplification. Or we could put our switch over on this side. Oversimplification. We can put our switch on this side, and then when we turn the switch on, we're heading back to ground, and that's called sinking the current. So that's what 1 and 0 really mean. So then that extra bit here, when the machine goes to discard that extra bit, it checks to see if it's a 1 or a 0. And if it's a 1, then that means we have the positive number. And if it's a 0, that means we have the negative number. So we need to turn that back into a positive number. So it should be a 2's complement number. So we'll subtract 1. You get 0, 1, 1, 0. is the ones complement. And then when we undo the ones complement, we get 1, 0, 0, 1. And then this bit that was discarded, that the computer already registered that we have a negative number. So it's a -9. And depending on the system, it's definitely in a RISC system. And I think in an x86, it'll just keep it in 2's complement if it knows it's a negative number. I'm not sure about ARM architecture or some of the other architectures, but depending on the architecture, it would probably just keep it stored as a 2's complement number and then use it that way. But it registered that it's negative, and it's a -9. So it still works out. The math all still works out because we don't have that extra 0 causing problems when we try to move back and forth on the number line. Yeah, the discarded bit is, so when the computer actually does it, when computers actually do it, the discarded bit of a 1 means that we have a positive number, and discarded bit of a 0 means we have a negative number. But the previous textbook that we were using for the class, when the quiz that you all will take for module 3 was written, defined it the way I wrote it on the board earlier. They said, let's use 0 for positive and 1 for negative. So, the questions on your quiz there are probably backwards from what the machine actually does. Great question. Great question, William, because that led to a little bit better explanation and better demonstration that that system works for everything. So, does anybody have any questions about that? Okay, we can address some beyond the scope of the course class questions about it. And again, if you're interested in the electricity stuff, one of the playlists of videos that I made, it's called Removing the Mystery or something like that. It's on our Ivy Learn list. It'll link to that. And one of the videos in there talks about what's called a full adder, and it steps through how the machine actually does this stuff. I think I actually built one in the video too. I put together a bunch of ICs and actually built one in the video. But that is what machines actually do. So that's how we process binary. I had one more thing on the list, which is the XSK system, which we'll talk about very, very briefly. That'll take like 2 or 3 minutes because it's a very subtle thing. So we'll do that next Wednesday, and then we'll talk about ASCII code and Unicode, because I want to make sure that there's plenty of lab time. It looks like we're coming down to just about a half an hour, so that took quite a bit longer than I thought was going to have to take today. But it seems like a good stopping point there, because this is something that the machine actually does, so that's an important one to understand. And I pointed out briefly that, again, just like our numbering system, that's not binary specific. We can do 2's complement on base 10, but it makes things harder when we do it on base 10. It doesn't simplify it. It works out really, really nice in binary. Makes everything nice and easy. But on base 10, it makes everything harder and more complicated. It just, it's that pattern goes with like the numerical bases. We can do it with any one of our bases. And if we do it with a different base, the complement is what we add to get to our highest digit. So like here, 0, we need to add 1 to get to our highest digit. And 1, we're already at our highest digit, so we add 0 to get to our highest digit. So any complement stuff works out really, really nice in binary, but any other bases, it tends to complicate things and make it messy and harder than it needs to be. But that seems like a good stopping point, because that's what the machine actually does. And I believe there are a couple questions on the quiz about that. So we'll make sure that you understand that process. And for those moving further into computer science degrees, those bits that for now we're just going to say get discarded do have important meaning. That's our, when you get to assembly language, that's one of our primary jump instructions in all of the main architectures, at least RISC, ARM, and x86. But any questions about that?
I don't have a question. I just want to let you know something.
Okay, so I'm gonna go ahead and wrap this up because I believe there was some questions that we're gonna talk about at the end. And so there's a little over 30 minutes left on our scheduled time. So as always, please spend that learning IT. I will be sitting right here until 8:50. If you have any questions, let me know. I can jump back on a Zoom call in a split second time because I will be sitting right here. Text messages and Ivy Learn messages make noise on my phone. Otherwise, you all have a great weekend, 3-day weekend. So no class on Monday because that's a holiday. And I will see you all next Wednesday.
Thank you. Have a good night.
What were you saying, Celeste?